Here I'm going to show you how to use a spreadsheet utility to simulate the Solow growth model. Currently, I'm working with Google Spreadsheet. It's available for free from Google Drive, but you can do exactly the same things that I'm doing here using Microsoft Excel. I'm working with an example that is a limited version of the full Solow growth model. The model that I'm working with has no population growth, but it does have growth in labor efficiency. And so you're going to want to extend the ideas that I'm showing you here in order to complete your homework assignment. Now, we want to consider how a change in one of the model parameters affects the dynamics of capital per effective worker, output per effective worker, and the other endogenous variables. I want to make a spreadsheet that is versatile so that I don't have to go back and change a whole lot if I want to consider how a change in depreciation affects the dynamics versus a change in TFP or a change in the savings rate. So I'm going to find it convenient to create two rows of parameter values for this model. One row is going to contain the initial values of the parameters. One row is going to contain the new values of the parameters. Okay, so I'm going to go ahead and highlight what I'm talking about right here. Okay. So you can see that every parameter that I've chosen here has an initial value which is equal to its new value. When we want to work with the model, then we can go ahead and go in and change the new value to whatever it is that we want. So for example, if we want to consider an increase in TFP from 1 to 2, we'll come in here to cell F9 and change 1 to 2, and there we go. Okay, go ahead and put that back to 1. Now the first thing we need to do is to create a sequence of dates. So we're going to come over here to cell I8, just under the word year, and type 0 for year 0, 1, 2, 3, enter, okay. And we could just continue doing this, but we want to take advantage of the spreadsheet's ability to recognize patterns. So in order to do this, I'm going to click on year 0, cell 118. I'm going to hold down the shift key and select cell I11, which contains the number 3. Now I've got these cells selected. These cells contain a representation of the pattern that I want to work with. I'll click on the small box at the bottom right corner of the selected cells, and I will drag down, and now I've got years 0 through 30 because the spreadsheet recognizes that I'm trying to count by 1, which is very helpful. The next thing I want to do is to create a sequence of labor efficiency values, and we'll see why this is going to give us something. We're going to learn something useful about how patterns are recognized by the spreadsheet. The first value of labor efficiency is just sort of given to us. I'm going to set that equal to 1. The next year's value of labor efficiency in year 1, is based on whatever the initial value of labor efficiency is. So we're going to create a formula. The equal sign indicates that we're writing a formula. It tells the spreadsheet that whatever we type should be evaluated numerically rather than just displayed as text. So I'm going to say equals, open parentheses, 1 plus the growth rate of labor efficiency, the initial growth rate, close parentheses, times the previous value of labor efficiency, which in this case was just 1. Press enter, okay, and we've got 2%. Now, I can highlight that initial value, or not the initial, but the year 1 value of labor efficiency. Since it has a formula in it, I can click the little box at the bottom of the cell again and drag it down, and we see that between years 1 and year 2, there was a 2% growth in labor efficiency. But then between years 2 and year 3, there was no growth in labor efficiency. Labor efficiency has stagnated. And we need to see why that is. So I'm going to click on the first year in which labor efficiency did stagnate. This was in year 3. And I'm going to investigate what the formula for that cell looks like. So I'm going to come up here to the formula editor at the top of the page, or the cell editor, and then look and see exactly what that cell is calling. It looks like that cell is correctly calling the previous value of labor efficiency in 10, which is right here. This is efficiency for year 2. But unfortunately, it's calling the cell E10, which is a blank cell down here. The spreadsheet has no idea that I have this initial parameter value and this new parameter value. The spreadsheet just thinks that if I'm going to copy the contents of one cell down, it's going to look at all the cells that that cell references and then copy those down as well. And so if I want to prevent the spreadsheet from changing the cell that it looks to find the growth of labor efficiency, I need to lock that cell. So I'm going to delete what I just created, except for the year one labor efficiency. I'm going to go back to my initial equation for labor efficiency. I'm going to lock the cell. So I'm going to say that when I copy this cell in the future, I'm going to tell the spreadsheet to not change where it looks for the growth of labor efficiency. I'm going to place a $sign in front of the column coordinate and a dollar in front of the row coordinate. Okay, so by doing that, it doesn't change the numerical result for year one labor efficiency. But now I can copy and paste. I'll copy down to year four. I'll copy it down to year four, to year five, excuse me. And we can see that clicking on the year five cell, even though the year five labor efficiency is calling on year four labor efficiency, it is still also calling on the initial value of the growth of labor efficiency. Okay, so being able to lock a cell is very important when you're trying to copy and paste a bunch of things, but you have a certain set of parameters that you want to always reference. Okay. Now, let's start working with the endogenous variables. Capital per effective worker is determined in the previous year. So capital per effective worker in year 0 was actually determined in year -1. Since we don't have anything, we don't have any information about year -1, as the simulators, we get to decide what initial value of capital per effective worker is going to be. Right now, I'm just going to set that equal to 1, but I'm going to come back and change that later. Okay? But the point is that we have the option of seeding the model by setting initial capital per effective worker. Output per effective worker is a function of capital per effective worker. So output per effective worker, I'm going to use a formula, is equal to total factor productivity, the initial value, times capital per effective worker, and all I'm doing is clicking on the cell that I want to be inserted into the formula. Then I'm going to raise capital per effective worker using the caret symbol to the alpha power, which is 0.3. Now, again, I want to make sure that I lock the parameter values, but I want to make sure I don't lock the capital per effective worker value in the spreadsheet. So I'm going to come up here to the formula bar. I'm going to place a $sign in front of the F to lock the total factor productivity coordinate. I'm going to leave J8, which is the initial capital value. I'm going to leave that without any $signs, and I'm going to lock the cell for the alpha term. Press enter, and not surprisingly, since TFP equals 1 and capital per effective worker equals 1, output per effective worker also equals 1. Now the change in the capital stock, this is capital delta. Obviously I can't use that symbol in a spreadsheet. The change in the capital per effective worker is equal to investment minus effective depreciation, or it's equal to the savings rate times output per effective worker minus the depreciation rate plus the growth rate in labor efficiency times the quantity of capital per effective worker. So I'm going to go ahead and write this formula in. This is equal to the savings rate, click on that, times the current value of output, click on that cell, minus open parentheses, the depreciation rate plus the growth in labor efficiency. If you had a model with population growth, which you surely will for the homework assignment, you're going to want to put the growth rate of population in here as well, but I don't have that, so I'm going to close parentheses times the current value of capital per effective worker. Now, again, I need to lock these cells because I'm going to be doing some copying and some pasting. So I'm going to come back up here into the cell editor, or the formula editor. I'm going to place a $sign in front of the coordinate for the savings rate. I'm going to leave capital without a $sign. $signs in front of the coordinates for depreciation rates and the rate of growth for labor efficiency. Press enter. Now, what I find is that the change in capital per effective worker is positive, indicating that a capital per effective worker value of 1 is obviously below the steady state. So there's going to be a little bit of growth transition towards a higher steady state, or a steady state that is higher than the current value of capital per effective worker. Okay. The next thing that I need to do is recognize that even though the initial value of capital per effective worker is specified by the simulator, by us, the subsequent values of capital per effective worker are determined endogenously. They're determined by the model. So the year 1 quantity of capital per effective worker is equal to the initial value of capital per effective worker, so I'll click on that cell, plus the change in the capital per effective worker that we already computed. Click on that cell. I don't need to put any dollar signs in here because this formula doesn't reference any fixed cells. It references relative cells. So I press enter, and now I find that for an initial quantity of capital per effective worker equal to 1, and given all the parameters that I've assumed, capital per effective worker in year 1 is going to rise by 6% to 1.06. Okay. Now, the next thing I'm going to do here is I'm going to click on output per effective worker in year 0. I'm going to click on the box at the bottom right corner, and I'm going to drag this down 1. Okay, so it's going to copy the contents of the cell down one row. It's going to continue to call on the same fixed cells that I've placed a dollar sign on, okay, but now rather than calling on capital in year 0, it's going to call on capital in year 1. So let's click on this cell and make sure that's what's happening. Or click on the formula editor and make sure that's what's happening. Okay. Sure enough, that is right. That is exactly what's happening. I clicked on the wrong cell. That's exactly what's happening. Okay. So look and see what's happening here. Output in year 1 is a function of total factor productivity initially, the year 1 capital per effective worker, and the initial quantity or the initial capital share of income. So the spreadsheet recognized that we always want output to be based on the current level of capital, but also based on the fixed parameters. I'm going to do the same thing with the change in capital. And so the change in capital is close to 0.06, but it's not quite 0.06. Okay, so this indicates that there is slowing growth as we transition towards the new steady state. Okay. Now, the spreadsheet makes things easy for us. So I can click on the year 1 capital, hold shift, click on the change in capital in year 1, highlight all 3 cells, and I'm going to drag these cells down to year 5. And so I can copy a bunch of cells down, and the spreadsheet's going to just know that it's going to know which formulas I want to keep where and so on. So that's great. Now remember, in year 5 is the special year. Year 5 is the year that there is a change in the parameter values. And so starting from year 5 going down indefinitely, we want the formulas to call not on the row 8 parameters, but we want them to call on the row 9 parameters. So year 5, capital, there's no parameters in that formula. We see that up here in the formula editor. So we don't have to worry about that. Year 5 output, however, is a function of parameters. So I'm going to come up here to the editor. I'm going to change all the 8s in the coordinates to 9s. Do the same thing for the change in the capital stock. Change all of the 8s to 9s. And now I can highlight the year 5 values, drag down, okay, and now I've populated capital per effective worker, output per effective worker, and the change in capital per effective worker all the way down to year 30, taking into account that there could potentially be a change in parameter values starting in year 5. Obviously, there are not currently any changes happening. Now, with this in mind, let's go back to the initial quantity of capital per effective worker. Now, I just arbitrarily chose 1, but a natural place to start is the steady state. So let me go ahead and do that. I'm going to type in the formula for the steady state. The steady state quantity of capital per effective worker we know is equal, open parentheses, the savings rate times TFP divided by open parentheses, depreciation rate plus growth in labor efficiency. Again, you would add population growth if that was part of this. Close parentheses, raised to, open parentheses, 1 divided by, open parentheses, 1 minus alpha, close. Okay, and so I have gone ahead and seeded the model with the steady state quantity of capital per effective worker. Since this is a spreadsheet, my change to the initial quantity of capital per effective worker is transmitted through all of the other cells for which there are formulas that are related. And you can see that the change in capital is always equal to 0 now. Output is always equal, or output per effective worker is always equal to its steady state value, and capital per effective worker is always equal to its steady state value. Now, let's go over here and see what happens if I change the TFP value from 1 to 2, starting in year 5. Press 2 here, press enter, and this is exactly what happens. We look and we see that in year 5 there is no change in capital per effective worker. That's because we're in the steady state, and capital per effective worker in year 5 was determined in year 4, before there was any parameter change. Capital per effective worker doesn't start to change until year 6. But output per effective worker does change. It does increase in year 5 because the production function shifts. So even though there's no change in capital per effective worker in year 5, since the production function changes, there is an increase in output per effective worker. And since presumably we're below whatever the new steady state quantity of capital per effective worker is, the change in capital per effective worker is positive, indicating that we're going to start transitioning, or the model is going to start transitioning towards this new higher quantity of capital per effective worker. Great. One other thing that I think is convenient, it may not be relevant for the homework assignment, but I like to keep track of the steady state quantity of capital per effective worker. And so I'm going to I could type in the steady state equation, or I could just copy what's in cell J8 using either Control-C if you're in Windows or Command-C if you're on a Mac. I can come over to cell M8. Again, this is Control-C if you're on Windows, Command-V if you're on a Mac. So copy and paste. Obviously, I made a mistake. I did not make a mistake. Well, excuse me. I did make a mistake, but the mistake involves the cells that I'm working with. Okay. So again, this is the problem when you don't lock the parameter cells. So let me go up and just lock the parameter cells in the initial quantity of capital. Everything is a parameter, so I lock every single thing. Now I'll try my copy and paste experiment again. Control-C or Command-C, and then Control-V or Command-V. There we go. Now I've got this steady state quantity of capital per effective worker. Okay, since this equals the initial value, obviously the economy is in its steady state. I'm going to copy and paste this down to year 5. Year 5, remember this is where there's a change in the parameter value, so I'm going to change all of the 8s to 9s. Press enter. Okay, and I find that in year 5, this increase in TFP, this doubling of TFP actually, has more than doubled the quantity of the steady state quantity of capital per effective worker. Now I can drag this down as well, and it looks like capital per effective worker is beginning to approach this new higher 5.58 value of capital per effective worker. It's going to be some time until that convergence actually becomes close. Now, let's go over to these other columns. We want to do the same thing that we were doing with the previous ones. When I come to labor efficiency, in year 5, I want to change the 8 to 9 so that labor efficiency is now drawing on the potentially new growth in labor efficiency, although currently it's constant. I'm going to drag this down as well, so I populate the rest of the spreadsheet. I'm going to scroll over a little bit, and I want to worry about some of these other quantities here. This is capital per worker. So columns J and K are capital and output per effective worker. Columns O and P are capital and output per worker. Capital per worker is just equal to capital per effective worker times labor efficiency. So I say this is equal, use a formula, equal to the contents of cell J8 times the contents of cell N8. I've got capital per worker. Output per worker is equal to output per effective worker times labor efficiency. Since these cells don't reference any parameters, I can just copy and paste them all the way down. And now I've got numerical values for capital and output per worker. What else do I have over here? This is the growth of capital per effective worker between the current period and the next period. So in this case, in the cell that I have highlighted right here, this is the growth rate of capital per effective worker from year 0 to year 1. We need to remember that we have the formula for this, and I'm going to go ahead and type this formula in. This is equal to the savings rate times TFP times the capital per effective worker raised to alpha minus 1 minus the rate of depreciation plus the growth rate of labor efficiency. And again, I'm going to come up here in the editor and make sure that I lock all of the parameter values and I leave the capital value unlocked because I want to allow that to change. Okay, so the growth of capital per effective worker is 0 in the steady state. That is not surprising. So I'm going to copy this down to year 5. In year 5, I know there's a change in parameter values, so I'm going to come up here, as usual, change all of the 8s to 9s. Okay. And so the growth rate of capital per effective worker in year 5 now is actually 9%. I can copy and paste this down. And what we should notice, is that as we approach the new steady state, the growth rate of capital per effective worker declines because the economy sort of moves more quickly early on, and as it approaches the new steady state, it slows down and slides in nicely into the new quantity of capital per effective worker. It does not crash into the new steady state. Now, the growth rate of capital per worker, we should remember this, is just equal to the growth in labor efficiency plus the growth in capital per, in fact, I'm not sure if I said that correctly. The growth in capital per worker is equal to the growth rate of labor efficiency plus the growth rate of capital per effective worker. So this is equal to the growth of capital per effective worker plus the growth of labor efficiency, which is equal to 2%. I'm going to lock the growth of labor efficiency cell so that initially the growth of capital, or for at least for the first, why is that looking that way? I know exactly why that's looking that way. For the first 4 years, the growth of capital per worker is just equal to 2%. It's equal to the long-run growth of labor efficiencies. In year 5, we need to change E8 to E9. There's been no change in the growth of labor efficiency, right? G is constant under the current example that involves just an increase in TFP. And so capital per worker is all of a sudden growing at a rate of 11%, up from 2%. The additional 9% comes not from growth in labor efficiency, but it comes from growth in the ratio of capital per effective worker. So same idea, I'm going to click on this cell that I want to to replicate, bring that all the way down. And now what I have is a set of columns. Now what I have is a set of columns that contain all the data that I need in order to construct the graphs that are required for the assignment. And so for the example graphs that I've created, I can come over here, and since the graphs were obviously constructed in advance, I just filled in the data. We get the transition paths for capital per effective worker and output per effective worker. An increase in TFP is going to lead to a smooth transition of capital per effective worker, but it's going to lead to a discrete one-time jump in output per effective worker followed by a smooth transition to the new steady state. Now going back to the parameters, the nice thing about having set up these two rows of parameter values is that now I can come in, I can set the new TFP value back to 1, find that the model is always in its steady state, and even though it's in its steady state, there's still growth in capital per worker, which means that there is long-term growth in capital per worker and output per worker. Come back to my transition diagrams. Since there's no change, since we're in the steady state, output and capital per effective worker are constant. Let's see what happens if there's an increase in the savings rate. Suppose we increase the savings rate from 15% to 25%. So I'll type in 0.25 for the new savings rate. Again, the model starts out in a steady state by construction, and all the data get filled in, and we find that an increase in the savings rate leads to no change in capital per effective worker in the year that the savings rate goes up. So there's no change in output per effective worker in the year that the savings rate goes up. But there's a smooth transition of both capital per effective worker and output per effective worker to the new steady states. So obviously, in order to answer the homework problems, you'll have to extend a number of things. You'll have to add many new columns that incorporate consumption per effective worker, investment per effective worker, and in other quantities. But everything that you need to do is essentially like what we've already done in this example. So hopefully this will get you started, and hopefully that you will find that extending this to the full model and to model to compute the paths of all of the endogenous variables should not be too much more challenging. So